Hello ladies and gentlemen, this is Free Home Brew bringing you the Mazegenerator as promised in the announcement video. This is the final product of the Mazegenerator. I thought I'd show you this one first because we can clearly tell what the colors mean. Black is a wall and white is the legal path. So whenever you want to solve this, you can use all the white squares to move in, and the black squares are illegal points. You can't move through the walls. The blue square is its starting point, so of the generator. You can start at any 2 points in this maze and get to any other point in the maze, but this is the starting point of the generator. So I'll just skip to that. We've got an orange square in its center. This orange square will carve the path from all the black squares. So all the black squares are, the entire field is now black, so it's all illegal. And whenever the orange square moves, it will leave 2 white points in its wake as to carve some paths through the walls. So it's got 4 purple squares around it. The purple squares detect whether or not the orange square can move into that direction. So whenever there's a wall beside the orange square, it will tell the orange square you can still move in this direction. Whenever there's a white square next to the orange square, it will tell the orange square you can't move in this direction because you've already been there. So yeah, that's basically it. Now, as for the backtracking part of this algorithm, whenever it changes direction, when it's not forced to, it will remember. So it will remember where it did so. So we'll see that in a minute. And whenever and those points are all added to a stack. So it's got a memory of that's shaped like a stack, and all of these points are added to the top, and it can revisit the topmost point, so the last point where it changed direction that wasn't forced. So let's see this in action. So the first move is down, and we can already see it's got 1 green square, and that's the point it will keep in its memory. This is the only square, the only point in its memory at this point, so the stack is 1 high, and the white square is a path. Beneath the green square there's also a white square, so that's a path as well. Because there's a path at this point, no purple square shows up, so it can't move back. It can, however, move in any of these other directions. So there's 3 possible directions it can move into. Like I said, whenever it changes the direction, it will remember when it did so. So because it doesn't change direction in this particular instance, it won't remember its point. So and at this point it will move right. So it will remember this point and this point and this point, and you can see the stack grow. If you were to visualize this, the stack is now 4 items high. So there's 4 points in its current memory, with this one on top and this one on bottom. Let's just see it move around a bit. This is an interesting part, because this is the first time it's going to make a forced move, and that's at this position. At this position there's only 1 move left to make, so it has to take this move. It has to make this move, and because it has to, it implies that there's no more moves left at this point when the orange square leaves this point in the next move. So we don't need to revisit this point because there's no more legal moves. At any point that's forced, any direction that's forced, that's forcing it to change its direction, will not be remembered, because I've just explained it's not worthwhile to remember. And same goes for this point, because this is yet another forced move. So let's just skip ahead to where it actually starts backtracking. These all work with the same principles. So this is where it first starts backtracking, and we can predict it will start backtracking at this point because when it moves to the left over here, we can tell it will run out of legal moves in this area, and that's because the area here is finite, so it will bump into itself at every possibility, and due to the nature of this problem, it will have to return to this point over here because it still has legal moves in this direction, and it can still fill up this area over here. So let's see that in action as well. This is the actual first backtracking that's going on. So when it moves down here, it will run into a dead end. It can't make any moves anymore. So whenever that's the case, it will return to the first previous state where it could. So this is now the top square on the stack. So when it moves down here, it will revisit the first point in its history where it still had decisions. So that's what it does over here. Let's see some more action. Some forced moves again over here and over here, and these two are forced. And finally we start backtracking again. When it moves up here, the first square in its memory will be this point over here, and because it can't make any more moves in this point, it will take this point into consideration in the computations, but not in the output. So you won't see it move back to this point, but you will see it move back to this point. It has taken this point into consideration, but because there's no more legal moves, it will instantly return to this point in the output, which is what I'm showing you now. So my prediction is that the orange square will return to this square over here. And again, when it moves up here, it will take all of these points into consideration, and the first square that still has decisions, still has legal moves left, is this square. So it will move back to this square. It will take the other points into consideration, so don't think it will just skip these. So here we go. Fill up this area over here. A little bit of backtracking going on. It cut itself off again, so it has to move down here and then return to this point. Let's see. There it goes. Some backtracking will be happening over here. A few dead ends. And this is a major leap. So it will move back through all of these points, and it will see it can't make any legal moves. So this is the first point where there's still legal moves. So it will move to this point over here. And continuing, yeah, because it moves in the to the left in this position, it finds a dead end. The next point in its backtracking history is this point, and it can't make any legal moves here. So the next point is this point over here, and then it can move into this direction. Well, because it moves it doesn't change direction at this point, so it won't remember this point here, and that's why it won't branch at this point, but it will branch at this point. So we can see that in action. See, between these two frames, this marker here is left out, and this square now belongs to this square over here instead of this one over here. So that's what we've just seen. And this is the next point, and this is the next point. Oh no, this was the next point. Okay, this is the next point, and it will return to this point over here. So the stack is now 7 points high, and when it moves into this direction, yeah, it will simply run into another dead end, and then it will take all of these points into consideration, find out there's no more decision left to make, and it will end up at the start position. Now when the start position is cleared from its memory, it means that there's no more moves anywhere to be made. There's no more legal moves, and in that case, if that's the case, the entire maze is done. It's complete. That's the end condition of this algorithm. So we're done, and that's the algorithm. I will be spending some time, I will be dedicating some time and some video footage to the source code, to the implementation. It's not a long piece of code, it's pretty simple, so you can be looking forward to that. Feel free to ask questions, comment, rate, subscribe, whatever. I especially like comments, so yeah, you can, I guess I'll see you guys in the next video. Bye.